Welcome to our fluid mechanics lecture with the topic rotating vessel. And in this video, we will solve two problems from the book Fluid Mechanics and Hydraulics by Gilisania. So here is the first problem, problem 4-16. An open cylindrical tank having a radius of 300 millimeters and a height of 1.2 meter is full of water. How fast should it be rotated about its own vertical axis so that 75% of its volume will be spilled out? So this is an example of an open cylindrical tank with a radius of 300 mm, or that is 0.3 meter. So 0.3 meter. And then the height here is 1.2 meter. So how fast omega should it be rotated about its vertical axis so that 75% of its volume will be spilled out? So it's full of water and then 75% will be spilled out. So that means the water level will become like this. This is the remaining water. Therefore, this portion here will become the volume spilled, or that is the volume of air. So we can say that volume of air is equal to the volume spilled. So this volume spilled here is actually cylindrical. So this is equal to, so that will be equal to this 75% volume out. So that means 0.75 of the total cylinder here. So that, or the total volume. So 0.75 times the volume of the cylinder, or the H here is the big H. So that is 0.75 pi. The radius here is 0.3 meters squared and the height is 1.2 meter. So volume of air now and also the volume spilled will be equal to 0.75 times pi times 0.3 squared times 1.2. That will be 0.2545. So 0.2545, that is in cubic meters. Okay, so since that is the volume of air, or that is the volume spilled out, so let's use the formula for the paraboloid to get the value of the omega. So we're looking for the value of omega here, the rotational speed. But before that, we need to determine what will be the placement of the paraboloid. Will it be inside the cylinder, or will there be a small paraboloid outside of the cylinder? So we will need to check via trial. So first, okay, so using trials here, so we have the cylinder at the radius of 0.3 meter. The height here is 1.2 meter. Let's assume that the paraboloid or the vortex created is inside the cylinder. So let's say this is the vortex or the paraboloid. Then this is the volume of air. Of course, this is the liquid. So if that is the case, our y here, or the height of the paraboloid, will be from the top to the vertex of the paraboloid. So we will check if this assumption is correct. So let's name this height of the paraboloid as y. And this is 1.2 minus y. So volume of air is equal to 0.2545 is equal to the volume of the paraboloid is 1/2 of pi radius squared and the height of the paraboloid. So let's get the value of y. We have here 0.2545 equals 1/2 pi 0.3 squared y. So what is the value of y? So y is 0.2545 times 2 over pi times 0.3 squared. So that is 1.8 meter. So y is equal to 1.8 meter. As you can see, this y here should be lesser than 1.2. So y should be lesser than 1.2 meter. So this is not the case, since 1.8 is greater than 1.2. Therefore, our assumption is incorrect. So let's go to the next assumption, which is actually the correct one now. So that means that there is a vortex outside the cylinder. So that means, okay, so this is the 0.3 meter. This is the rotational speed. This is the h, 1.2 meter. Therefore, there will be a paraboloid outside the cylinder here. Of course, if this is an open tank, so that means the water will be spilled here, spilled out there. So there will be an imaginary curve here. So there. Therefore, we have here two heights of paraboloid. The first one is the height of the paraboloid that is bigger, and then the height of the paraboloid which is smaller. So let's name this as y1, and then this is y2, the smaller paraboloid, which is actually this y2 here. So let's write here, this y2 is actually equal to y1 minus 1.2. Now, how do we get now here? What do we need to get here? So we need to get the value for y1, because from the formula, y1 is equal to rotational speed squared, the radius 1, which is radius 1 here is the 0.3, and the radius 2 actually here is the radius of the smaller paraboloid. So here is the R2. Okay. So this is from the formula, this is y1 equals omega squared times r1 squared over 2g. So we need to find the value of y1 because r1 here is given, course, we have here as given, and we're looking for this omega. So how do we reduce the unknowns? We have here 3 unknowns. So we can use the squared property. So by the squared property, so we have the radius R1, which is 0.3 squared all over the height of the paraboloid y1 equals the R2 squared over the height of the smaller paraboloid y sub 2. And we know that y sub 2 is y1 minus 1.2. So this is 0.3 squared all over y1 equals r sub 2 squared all over y1 minus 1.2. So we get the value for r squared or r2 squared equals, that is 0.3 squared is 0. Let's check that. 0.3 squared 0.09. So 0.09 times y1 minus 1.2 all over y1. So we have here, we're going to use this r2 squared for here. Now remember, the air, so this is the air created by this vortex here. So V air, volume of air, is equal to the big paraboloid, volume of the big, say big par, or the big paraboloid, minus volume of the small paraboloid. So we have the volume of air still unchanged, that is 0.2545 equals the volume of the big paraboloid, which is, the formula here is 1/2 pi the radius r1 squared and the y1, then minus 1/2 of the pi r sub 2 squared y2. Okay. So 0.2545 equals, it is 1/2 pi r sub 1 is 0.3 squared the y1 minus 1/2 pi the r sub 2 squared. Take note, it's r sub 2 squared. So we will insert this in the formula. So 0.09 times 1 minus y sub 1 minus 1.2 all over y sub 1. Then finally we have y2. Now we know that y2 here is y1 minus y2. So this is y1 minus 1.2. Okay, so as you can see here, we now have only one unknown left. So we can now solve for the value of y sub 1. Let's we can solve this directly already. So y1, so using the calculator, using shift solve, is 0.2545 alpha equals this 0.5 of shift pi times 0.3 squared times alpha x minus 1/2 of shift pi, and we can already delete it 0.5 shift pi times 0.09 times, so we can multiply it here, which now becomes alpha x minus 1.2 squared all over alpha x. Oops. So alpha, it should be close parenthesis. So shift solve. So value of x now is 2.4, or that is y1 equals 2.4 meters. So since we have now the value of y1, we can now use this formula. So y1 is 2.4 equals omega squared. R1 is 0.3 squared all over twice of the gravitational acceleration. So omega now is equal to, or it is omega square root of 2.4 times 2 times 9.81 all over 0.3 squared. So that is 22.87 rad per second. So 22.87, that is rad per second. Now if it is asking for the value of the rotational speed in RPM, you just have to multiply it with 30 over 5 so that you can cancel the rad there. So what's left here is to multiply 22.87 times 30 divided by shift pi. So that is 218.4. So that is the W, or omega is 218.4, and that is in RPM, revolution per minute. So this is the answer in the book. Omega is 218.4. So that is problem 4-16. Now of course there are other way of solving this, but this is the way that I find easier, or that is so that is 218.4. The second problem here is 4-17. Now this time it's talking about discharging 1/3 of its content. Now let's solve this using the same method in the first problem. So problem 4-17, an open cylindrical tank 1 meter in diameter and 3 meters high is full of water. What speed in RPM must it be rotated to discharge 1/3 of its content? Okay, so here is the open cylindrical tank with the diameter of 1 meter, therefore it will have a radius of 0.5 meter, and the height here is 3 meters. It's full of water. Now it rotates and it's looking for the speed of rotation omega here, and it says here that with its rotation it must discharge 1/3 of its content. So just 1/3 of the content. So this is what's left, the 2/3. So this is the volume spilled. Then this is the air, volume of air. Therefore, we have here volume of air equals the volume spilled. Now, the volume spilled is 1/3 of the total volume of the cylinder, pi r squared big H. So, 1/3 of pi 0.5 squared times 3. So, volume of air now is equal to, so that will be shift pi times 0.5 squared times 3 all over 3. So, volume of air is pi over 4. So, let's preserve the number. So, let's just use here pi over 4. Pi over 4 cubic meters. So, let's have a trial first. Let's just assume that we're not sure, or let's say we're not sure if the vortex is inside or there will be a small vortex outside or paraboloid. So, we'll be having the first trial here. And our assumption here is the paraboloid is inside. So this is our assumption. Again, our radius here is 0.5. Height is 3 meters. This is the omega. And let's name the height of the paraboloid as y. So let's check if the value of y is less than 3. So that's the goal. Y should be less than 3 in order for this assumption to be correct. So volume of air. So again, volume of air is this one here. So V air is equal to the volume of the paraboloid. The paraboloid being 1/2 pi r squared y. So that is V air as pi over 4 equals 1/2 pi, radius of 0.5 squared, and then y. So what's the value of y? So let's cancel the cancel off the pi here. So y is equal to 2 over 4 times 0.5 squared. So y is equal to 2 meters. Now this 2 meters is less than the height 3 meters each. So that is correct. The assumption is correct. So we will now use the scenario wherein the paraboloid is inside the cylinder. So what's next here? So again, let's put here trial. So we did here a trial. Okay. So since the assumption here is correct, so let's use the formula of the paraboloid y is equal to omega squared r squared over 2g. So y here is 2 meters equals omega squared, radius is 0.5 squared all over twice of the gravitational acceleration. So omega is now equal to square root of 2 times 9.81 all over 0.5 squared. So that is 12.53. 12.53, that is rad per second. Now we're looking for the answer in RPM. So let's multiply it with by 30 over pi, so as to cancel the rad here. And what we have for the speed is 12.53 times 30 over pi. So that is 119.65. So 119 omega is 119.65 RPM. In the book, the answer there is 119.64, but that's just a minor difference. The difference came from the rounding off of the values, so it's still correct. So that's problem 4-17 in the book Fluid Mechanics and Hydraulics by the author Gilisanya. Okay, so that's all for this video.